Awesome. So hello, everybody. My name is Kevin Kochek. I'm the founder CEO of Chemical Q Device. This is discussion 107, Thursday, November 2nd, 2023. And this is for quantum-inspired machine learning algorithm architecture, R&D, new utilities, and higher accuracies. So definitely a lot of exciting stuff here. So I wanted to start off first. So this is just the general outline of the talk. The next slide has a lot of pertinent information put in graphical form. So I'll be going over what it means as far as simulator specific, significantly better performance versus classical ML, and then also the need for new utilities here. Now, the next one, OpenAI basically has some of the weaknesses of the current gate model. Current gate model is old. It's like 2005. I think it was first implemented in like 2012. It's meant to run on hardware and simulators. So that's where you see kind of like the not much of gain that we get with gate-based. And then two of these articles are very interesting. So this first one, this massive parallel quantum computer simulator, this is 2006. So these aren't machine learning, I don't believe at all. So it's more like running the circuits. And then 2018, so 11 years later, they updated it. So I'll update that as well. And then also going into, this is already being scaled up in industry, right? So it's a working technology. NVIDIA in specific has done, 4,000 GPUs with, some form of quantum inspired ACM article, and I'll get to a lot of these. This is towards the end, so short presentation today. And, also kind of wrapping this up with GitHub, there's leading code repositories. Mine's one of them that does a lot, with medical and other stuff too. And then kind of the wrapping it up with the momentum that we're going to see, very likely with this technology. So this is the first diagram that I want to go over. So this is basically like, if we have everything, and I'll start with the left, with a quantum processing unit, or i.e. a quantum computer, my forecast for it is over 5 years to get readily available, error-corrected quantum computer with accurate and efficient QML workflows. You'd likely have to see significant engineering in order to sync this up, with classical, which you would have to. So right now we're at partial error mitigation, and then, forward accumulation method. It's a type of differentiation that's used, and it's basically for more parameters, it goes exponentially up in time. So it's not, I would say like a working technology yet as far as differentiation. The outputs you're trending, and I haven't seen it any other place that you would actually get exact answers right away. Particularly, you have to take a lot of shots, and in a machine learning workflow, that's just not, for a specific task, it has to return right away. And so that's another prohibitive thing. And of course, if you're dealing with error of any kind, you're dealing with density matrices. So the mathematics behind this is actually not on the surface of the block sphere, it's on the inside. So you're not in this pure ket form. And then, of course, you wouldn't be able to get to any kind of pure, any kind of QML workflows with these conditions. It's a continuously updating process. If you have, say, for instance, for a single epoch, if you break it into, 10 mini batches, that's 10 times that you need to update parameters for that epoch. And you could have, dozens, if not hundreds or more epochs. So that's where I put that. I'm estimating this technology, with quantum computers, in a practical workflow with QML over 5 years from now, and that's probably conservative. Now, what is working, and many people, you just assume like you get these quantum machine learning, demos, and your CPUs and GPUs are available. Now, what's basically the hope for the future is move into different architectures, because right now we're getting about the same, if not a little bit better performance. Sometimes they'll say, a different utility because we, strain things X, Y, and Z. But in my opinion, there's a lot of juice left as far as like, not just having these, standard gate-based, models, and then moving into more towards like, okay, this specific, you're getting, this is big data, everything on the right that you can do. It's slowed down, but it's big data. Getting into other different types of architectures that aren't this, based since the turn of the, 2005, basically. So the good thing today is actually we have reverse accumulation, which is a type of backpropagation. So backpropagation is synonymous with classical machine learning. And what they term it with the quantum circuits now is this adjoint differentiation. So we have that. And our outputs, we can output exact. They said, I think for every model, you can do it like this, but sometimes if you want to do probabilistic, you can as well. But basically, like, it's like if you were to rethink quantum inspired machine learning, it's not as complex as you think it is, because it's like the linear algebra, is just for, the qubit here, the simulated qubit. And you can actually do classical algorithm and a quantum algorithm in a single device. This isn't done as much because you typically need, more RAM. And that could be another prohibition with the gate-based model as well, moving forward. And of course, we have pure quantum states, so this is, despite the simulation process itself slowing things down, this is a preferred ket notation. And this is basically, you're on the exterior of the Bloch sphere with this. So all of this winds up that we have quantum inspired machine learning workflows. They're considered classical data generating, classical processing. And it's basically like the whole thing is hinging on the physics of quantum mechanics, right? Finding better ways to get new utilities. And I don't think we're there yet, based on the papers that are coming out or have come out, and then improving this performance that we've been seeing, like I said, it's typically as good, maybe a little bit better, but, it's not different, significantly better. So here's what I believe for the next step. So basically, we need a simulator that's specific to quantum circuits just for simulators. Okay. There's a theory, and it's a very strong theory, that all of this motion, and in my estimation, will be over 5 years away, should be going towards eventually it'll work on quantum computers. Now, I think we can get even greater gains focusing on simulators and not designing things so they also have to work on today's hardware to some extent, because it's just too far away. I think it's going to be hard to prove that this is, anything less than 7 years, 10 years, something like that, with the quantum computer, the other things that you need for effective machine learning. So you're going to require, to jump to these next stages, like I said, it's not a full attention on quantum inspired machine learning. It's more like, we just have to be in the ballpark. So when we get the awesome hardware, but then you have the other issues. That's the sense that I get with this. So sticking with everything's on CPUs and GPUs, we need significantly better performance versus classical ML and these new utilities, driving things forward as well. So this is a summary. It's based on OpenAI, but this is, these are some of the disadvantages. And of course, some of these, it will actually say like, okay, and if for hardware and stuff like that. So I'm not necessarily focusing on that as much. So basically, disadvantages is gate-based quantum circuits can require many resources to perform useful computations. Not all quantum gates are universal and may not be sufficient to perform quantum computation. Mapping, and this kind of shocked me here a little bit, or not shocked me, but it's like, okay, like something like that's not practical. Mapping high-level quantum algorithms to low-level gate-based circuits can be non-trivial. So again, as far as what's in the work, post-gate model, because gate model is problematic for quantum computers too, right? And moving to the next steps, with simulators, so we don't require nearly as many, resources because we don't have these, emerging machines. That it should be a full-on thing, right? Like I'll show you later. NVIDIA, these massive, like, Brookhaven National Labs scaling up, QiML type of experiments throughout the rest of the year. And this mapping process can lead to inefficiencies and longer compute times, and then exponentially increasing number of gates plus qubits to simulate more complex quantum systems. So the advantages of quantum speedup are highly problem dependent, and then and gate-based quantum circuits may not be the best choice for all simulation tasks. Are there any questions at this point? So I know some of you are, people keep coming in, and I'll probably go back to the original, this page 3 diagram that kind of like breaks it down. Everything is like, okay, we should be moving forward as an industry, and some are have already taken that step. Wall Street Journal, Sandbox AQ, these types of things. So feel free. So you can either raise your hand, or you can. Let's see here. You can put it in the chat as well. Okay, so this is the first paper. So I'm covering 2 papers today. So massive parallel quantum computer simulator. So this was done with Fortran 90. Now this, and the following paper after this is 2006, and the following paper is 11 years later, which would be like 2018. And I would say Penny Lane, really hit their stride. And I want to say like 2019, especially with models. And they still have this quantum transfer model that has like, all these working components. That's just like, if we could only get better accuracy, and hence, we might need a better circuit architectures. But basically, they call it portable software to simulate universal quantum computations on massive parallel computers, simulating up to 36 qubits using 4096 processor, and that's taking up to a terabyte of RAM. Now, I think for both these papers, they're not machine learning workflows. It's basically, as far as I could see, just running the circuit or evaluating the quantum circuit. So the simulator exhibited nearly ideal scaling. So as a function, as a number, so increased processors, it scaled correctly. Simulator software may also serve as a benchmark for testing high-end parallel computers. So this is basically saying, like, you already have benchmarks for HPCs, and now this may serve as another one. And then the OpenMP. So I've used these. I've used OpenMP. I haven't used MPIs. So anyways, OpenMP code is up to a factor of 2 slower, so 2 times as slow as the pure MPIs. Now, MPIs has been in the news this week. There's in Dell, and I think there's some transition to some advanced form of, this is all considered massive parallel processing when you're talking about open MPIs, and you can have it's basically, you can have, I forget this term, but basically you can do open MP, and then use it inside Python notebooks. And then MPIs are very synonymous with multi-node GPUs. Okay, so keep in mind this is 2006. So as a consequence, also the MPI OpenMP code, because it has OpenMP code, is slower than pure MPI code. So it's just interesting to look at these things. And again, these are like, even behind, some of the standards that we have for, running machine learning, definitely back in 2006 with this. So here's some of the devices. So keep in mind, we're looking at, the software is based by I don't think there's anything wrong with that, Fortran 90. But anyways, these are the devices that were available. These are supercomputers. So SGI Altix, and you have two from IBM, Hitachi, and a Cray right there. So you see the CPU clocks are a little bit slower. Now, I believe, because this is the only one I could find in this specific paper, this is the circuit that they kept evaluating, and it's not much. So it's all of these are 2-qubit gates right here, this whole block, and then you have a bunch of these, XX, YYs, these things here. So definitely an interesting paper, but it's taken some time. I wouldn't say that this was rapid, evolution from this paper to, the formation of, Qiskit and Penny Lane and these types of things. But it's good to see on paper. So here's the second paper, and they call it Massively Parallel Quantum Computer Simulator 11 years later. And, here's, the benchmarking to benchmark gate-based, here we go, gate-based quantum algorithms with powerful supercomputers that existed back in 2018. So this is before the first, big waves of Penny Lane models available to consumers to use. And there's not a huge, yes, you need the RAM and everything, and we have even more RAM today, but like a lot of these principles are synonymous with the challenges that we have today, with the quantum inspired. So, they said they did up to 48 qubits on this specific supercomputer, the Sunway Tahoe Light, and on K computer, and exhibited close to ideal weak scaling behavior on the Sunway. Now they presented this as a positive thing. So same behavior on some of these other supercomputers. So for 45 qubits, you needed a half a petabyte of memory, which is substantial. But again, I think with both these papers, there definitely didn't mention machine learning, anything like that, but I think it was more like just run these huge circuits. And this is the gray area that people talk about as far as like, yes, we can get, huge qubit counts with simulators, but can you actually run, efficiently with QML workflows there? Okay, so this next slide is JU, so they call it like Jukes, and it's a simulator ranging that you can run it on personal computers to the largest supercomputers. And of course, these things are just like well-known, we can do this, separate penny lane, quantum simulations on our laptop, and you can download penny lane and all that kind of stuff. So this is kind of this setup before, like I said, penny lane got big and Qiskit got into this. And you'll see this first one, so Jukes E, numerically exact. So for this one, it's basically, more accurate, up to 45 qubits. The next one was Jukes A, which is this approximate. So to do this, they got up to 48 qubits on less than a petabyte of RAM. And to do this, they employed this 2-byte to represent the quantum state in terms of 2-byte numbers. So there's little tricks that you can do, like, you just typically do everything traditionally classically, but like there's just, things you could do from like a 2-byte, and I've seen, 16 and these types of things too. So it said this A1 effectively reduces the memory requirements by a factor of 8. So it might not seem much, but typically in these ML workflows, we'll be at like 30 qubit max for like penny lane, multi GPU with NVIDIA as an industry. And again, I don't think this task is anywhere near what we're talking about for ours. So you could see, like, people say, well, how many qubits can you simulate with simulators? And this one, 2016, 2018, and they're up to 48 qubits, but I don't think the task is like a continuously updating, parameter workflow that you would see. So for this particular one, they say in general, Jukes is a revised and extended version of the simulator, and it's still in Fortran. So I know for sure that a lot of the devices today are written in C++, okay, and maybe even other things too. So I have not seen Fortran and these waves of devices or simulators that we use today. Now, this term simulator is typically like, we need RAM, this device is dedicated to it. And you can easily, from what it sounds like with penny lane, you can easily do quantum and classical algorithms, same device, without calling things, separate simulators and those types of things, but typically with less RAM, if you're sharing things. Okay, so, basically, they use the same MPI communication scheme, as you can see from before. It was a lot better than Open MPI, with to use MPI. And again, 2023, now MPI is facing, changes, and I is trying to make sense of the email kind of quickly, as a Dell email that I got. So, okay, so this is based on some data. So we have all the supercomputers here. And again, their Sunway Tahoe Light is the one that trended to do the best here. And the biggest thing that shows up in these charts is how far you can go with qubits. And as you can see, these are more efficient techniques. So it is possible that some of this turns into a lost art. And then people forget that you could do things like 2 bits versus 16, and cut the memory requirement basically by 8. It's possible. But you see here, these are not ML workflows. These are, and again, this circuit, I believe is the first one. I'd have to double check, but you could see that they're going a lot stronger here with, you basically want to be lower on this left one. So say, for instance, this K computer versus, actually K computer did a little bit better in this case. And then you can see here that the Sunway Taihu light that they were running, this is 2018, is lower than the K computer here. So I read these papers in order to get additional insight into it. And some of them are old and they're not publicly available and these types of things. So I'm happy with what I got from there. I think the things that I'm looking for is basically like, to talk to these leading, people in organizations that have been pushing it, with quantum inspired, and a lot of things, you can do quantum inspired and they want to go to hardware, but I want to focus on the simulators for sure, as far as research, no noise, no effect to patient data, that type of stuff. Okay, so this is the past 365 days with the technology. So as you see this first one with NVIDIA, these are actually V100s. They're like clusters. So if you click on this link, I'll have all this up and it'll be, available. Is basically, 4,000 plus of these V100s and then A100s to mix in to do quantum state vector. Okay, so there's different types, but the two main ones you'll hear is quantum state vector. You'll also hear about the tensor network. Tensor network trends to be a little less functional, but you can go higher in qubits with that one. So that was December 15th, 2022. So actually, it's a little bit longer than a year, but it's about a year. And by Lobo et al. Now, this next one is very interesting, and I would highly recommend it if you're coming from a classical background. And basically what they did is they took a single A100 GPU, and they said that the performance of it, in order to match the performance of today's A100 GPU, it would take a QPU with 10,000 error-corrected qubits. I think these are actually even logical. And then with 10 microsecond gate time in the upcoming decades for that specific one. And their main conclusion in this, and this is like one of those things where it's just like, it's a release every single month. So it's May 2023. And these three authors are, seem established in their fields. The QPUs, will be for big compute and for small data, right? And typically when we're talking about ML workflows, we're not talking about small data. We're talking about massive data. Now, this next one is interesting. So Penny Lane, NVIDIA National Energy Research Scientific Computing Center, and Brookhaven National Lab are scaling up with GPUs and supercomputers, accelerating massive simulations of quantum systems. And this is going on through the rest of the year. And this one came out kind of recently, so September 12th, 2023. And I think as far as the highest scope, because NVIDIA, and trust me, NVIDIA has probably run a lot more than this, than what's been published. But this is good to see. This is a huge collaborative, there's several sets of experiments. And like I said, they'll be scaling this up. So the technology is not only readily available, it's, and working, is that they and others are scaling up the technology. So this next one, so the Wall Street Journal, so this is September 21st of this year. And this is, the name of the headline was GPUs Transformed AI, and now GPUs for Quantum. So Sandbox AQ is using GPU, so they say quantum equations, quantum software on GPUs. Okay, so I don't know. It's a matter of months, maybe. That would be, logistic, but it'll all come down to the results. So same thing if I'm running, single node, GPU, Penny Lane, models, or that they put up on their website. And I'm not getting statistically better accuracy than classical models. And I'm not getting, different types of utilities. And that might be available today to some extent. But the risk versus the reward for quantum inspired is the reward is much greater, in my opinion, than the risk, right? The hardware is readily available across the board. I'm not seeing GPU shortages. Like if I run on Colab, I can run on like, A100s and, V100s or TPUs or those types of things. So I personally believe that all of a good portion of the development being focused on quantum hardware should shift into quantum inspired. Now, yes, maybe we'll come back to it in 7 or 10 years, right? But like the primary application is quantum machine learning. And, it's just, it doesn't make sense to have so much of the workforce working on error correction or working on scaling up qubits, these types of things when we have it now, and we can make a huge impact, especially if we understand quantum physics better with large data sets. Okay, so this next part is GitHub. So I'm huge into GitHub now, so I'll still keep my link to but basically, this is where the rubber meets the road. So most of, if not all of these, well, some of them are like lists, have the actual notebooks, and I put everything up. All my stuff's up there, like as far as like what I've published, notebooks, it's all up there. FDA studies, that type of stuff too. So we'll get into the Penny Lane, and Penny Lane has multiple repositories. So the biggest thing that shines for me is the torch layer. So torch layer is basically the bridge to, if you have existing PyTorch classical models, you can now define your your quantum circuit as a torch layer, and then insert it right in the middle of other torch layers. And then so that's that. And then if you have the other, I think it's reverse, it's either reverse or forward passes, the one right below it, you have to fix that part too. So Qiskit machine learning is run by Qiskit community, and it's basically the same. They also offer their Torch version, Torch connector, and I've optimized some of these their models using that specific option right there. And then you also have TensorFlow Quantum. Now, TensorFlow Quantum is a little quiet on my end, like I don't see a ton, but I think it's an active, like Owen Lockwood over here. He does TensorFlow Quantum, and he's done like 30 something discussions on TensorFlow Quantum. So anyways, the circuit for TensorFlow Quantum, you have to use Circ, or traditionally you would use Circ, and you can take advantage of Keras and TensorFlow too, to assist with TensorFlow Quantum. So anyways, there's a bigger following than I thought with TensorFlow Quantum. Now with this other one, tensor-based quantum machine learning builds on top of TensorLee. So this is previously available, and PyTorch. So this author is TensorLee, and then you just find these things. Now there are a number of, they're just like static, but there are a number that are just actively involved. So say for instance, with some of Penny Lanes, they might have over 4,000 stars, and equivalent numbers of forks, is basically to fork your stuff there. And then so here's Owens. So this is the other, he's an expert in, I would say, multiple different quantum languages. This specific one I picked because it's a curated list of papers, blogs, and research in QML. So his handle is Lockwo. So it's just LOCKWO. It's a little hard to find. And then of course with mine, so I've done a lot of work with this as far as different libraries. So I've got Qiskit, Penny Lane, Circ, and specific, like, these are open access, drive the industry future. I don't view much of them. Like I basically see that we need to go to the next level with architecture, with circuits. And a lot of the work is just like as good or a little bit better, just like the rest of the industry, So it's just basically to propel into. And there's actually a fair amount of, medical R&D, and then a lot of FDA studies as well. So here's the handle. It's Kevin Kochek. Okay, so wrapping this up. So basically, if this is static, we're basically wasting a lot of energy, because basically we have an established technique of, quantum machine learning, quantum inspired. And basically, people are already scaling it up. I don't know what their notebooks are, so I can't tell, it'd be great to see. But basically, greater understanding with big data sets. Because like you'll see specific papers, that come up, they just trickle out and they'll just say like, well, you have to change the data set, have to change the algorithm based on every single different data set. So I hope we're not stuck with that, but it's just, there's not, I mean, there's a fair number of researchers, but it's just like, there's other stuff going on with the field as far as quantum computation. And I could convince other people to switch to QiML, because if you want to run it on real hardware, people will still be working on that, but give it 7 to 10 years or something like that, at least over 5, and get stuff done today that's productive, and waiting for results for these, the 4 from industry. So basically this model was introduced in 2005. I don't have free access to this specific one. This is IEEE. It'd be worth taking a read, for sure. So that's 2005. And like I said, I don't think they started truly implementing it until 2012. And especially, with the Penny Lane stuff, and with Qiskit, you're talking at least, 2018 later, until the stuff became, more mainstream, how it is today. And then, the core of this is basically, we have quantum mechanics, we have quantum physics, and we have bits, and we have data sets. What's a different approach of going by that to get better accuracy and better utilities? And then, so here we go, path towards new utilities, identify specific utilities or solutions only available to quantum simulators, okay? So, it's just, you have to work with working technology. Like if it's just not working, if it's many years out, it's like these could be saving patients' lives. If it's something that's a new utility, it's technically the same thing as how things are. It's just, a quantum library, bits are behaving by quantum physics. That this could be helping people around the world and speeding up, or improving accuracies of other machine learning workflows, in other industries too. And basically this rethinking stage, right? Because everybody gets stuck in just running experiments, and you're just like running for months. And, I'm talking like Jupyter notebooks, those types of things. And you have to quite like, if your results aren't significantly better and it's just like working, don't be afraid to ask or to chime in, because to other people it might be just, this is as good as the industry should be, and to other people that have like time sensitive, or like sensitive to, we can't have any noise whatsoever. So like data that's like patient data that's like it can't be exposed to any type of noise, especially like for inference. But don't be afraid to speak up, right? Because do your research, and this is what I found, and it's backed up by industry scaling this up. So, and financials, $5 billion they say by the end of this decade, 2030. So, going from like a Linnet to an AlexNet, I don't think we're quite there as far as hyper quantum computing, as far as like everything is efficient, always better results. So for those that don't know, a Linnet is more like MNIST data sets, like 0 through 9 numbers. And an AlexNet is more like 1,000 classes. I haven't seen anything, like efficient like that for QiML quite yet. And then a ResNet, is like the next one. So you can have like a 18, 34, 50, these types, and up to over 100. And that means the number in general, like the layers, so ResNets, more advanced than your AlexNets. Okay, so this is basically it. Like we have all of this data, and these are huge companies. NVIDIA, I don't know how they are right now, but probably at least Fortune 100, something like that. Their technology with GPUs is running the world. ACM is basically, an established organization, and it put together this like, you have to, like, in order to get to an A100's performance today, you're talking like tens of thousands of qubits, and it's not just qubits, it's other things that it doesn't have, like for quantum hardware. NERSC, Brookhaven National Lab, doing this, scaling up of, big quantum experiments with GPUs. And then Sandbox AQ too. So they had some medical news. They're doing some stuff in medical. And, basically, I think this is where it's at. I mean, I think the research really shows. And for those, and I'll have this up. Well, first one is this. So, the research shows like there's a focus using GPUs, bigger experiments, quantum circuits, updating machine learning kind of stuff here, so NVIDIA does other stuff, with so they'll try to get QPUs and GPUs to talk to each other. But I think for anything like, patient data and, sensitive data, you're not talking anything with like a QPU for some time. So yeah, so if you came in late, and then so all this will be up, and this basically shows that we have working technology. It's being scaled up. As far as the mainstream, as far as the tools that we have access to change, circuits and stuff, these, core algorithm architectures have to be changed in order for us to start seeing, benefits. So like I said, like people can get settled, like it's a working technology, it works as good, a little bit better, proof of concept, but it'll take some work, to get it to other levels. Are there any questions regarding any of the slides with this? And then so I saw other people come on here too. So feel free, so you can raise your hand, you can put into the chat as well. And I also see people from previous discussions too. So yes, it is great and exciting. And I think, like it'll need some more, like as far as like, I don't know if these like, I don't know, if they say they have a lot better results and are good at documenting it. And I mean like the NVIDIAs and the Brookhaven National Labs and Sandbox and these types of things, is that will substantially, in my opinion, make the industry move faster. So you could do cool studies. So you can do cool studies like comparing algorithms, like substitute this for this in like Qiskit or Penny Lane model, and that it'll show you the differences. But your very best, will not likely be, because we're kind of stuck in this architecture right now, your very best will likely not be much better. It maybe a little bit better than the classical, purely best classical. So I think that's the thing. Just take care of it now. Like just, if we get better results, like how well is it compared to the purely best classical, because why come back 6 months and say, okay, you have to run classical models, right? And get the best results that are possible and document it and then compare it to your quantum hybrid. So yeah, high levels of detail, I would say. Are there any questions at this point? So obviously the last 2 weeks have been more of the FDA and like how could this fit in with quantum, which I don't really see an issue. It's basically an understanding of like, it is the same thing. It's just you need a different library, and then it's like the bits are acting in different ways. So but yeah, any questions or comments? I mean, we only have 8 weeks, for the rest of the year. I know that sounds, kind of interesting to a lot of people, but as far as starting to get some work done, I appreciate, all of the, basically recommendations and word of mouth, for the technology in my startup. And, definitely I kind of see it going up and up, especially when somebody kind of breaks the news, like they've, found a different way of doing QiML. Yeah, so obviously, this talk is meant to kind of like encourage the field and trailblaze through this stuff. And then I don't know, and then Edwin or Edwidge, you could come on as far as being a little bit more specific, because you had mentioned accuracies are not too good if the hype the influence and links. I mean, now are you talking about real hardware, or are you talking about like QiML, like quantum inspired? Go ahead, Ron.
Hey Kevin, how are you doing?
I'm doing good.
Good to hear. Just curious as if you have any plans to start looking at some of the new hardware that's come online, um, specifically the Q era 256 qubit neutral atom machine, and see what sort of performance improvement you might get out of using that many real qubits.
Yeah, I mean, unless it's for a very specific purpose, like outside of a traditional QiML workflow or QML workflow or machine learning workflow, I don't see any hardware technology because of the noise and the other four factors that I had mentioned. I don't see anything really available for quantum machine learning until at least 5 to 7 years.
Yeah, well, that's why I'm asking about QEra, because neutral atoms have a much lower noise profile. They have longer coherence, so their usable quantum volume should be up there. I haven't investigated what their noise mitigation techniques are. Uh, we all know that anybody who's used the IBM stuff, we know that what they're all about right now is noise mitigation and noise correction, error correction. But some of these different technologies don't have the same issues. So uh, hopefully their noise mitigation and their error correction tasks are much smaller. And, again, you get 256 qubits that you can use now as opposed to 5 or 7 or whatever you can get for free.
Yeah. And I'm not really putting any of them in quantum machine learning or machine learning workflows. And they will, you'll get big problems with small data, smaller data sets with some of quantum in the next couple of years. So I'm not as concerned as far as like, if neutral atom or gate-based superconducting or ion trap can pull off a big problem. I think that's totally within realm, next couple of years. But this is not the principal application for quantum computing. And I think that's where the industry kind of doesn't understand this is like, quant or machine learning is done by millions, probably millions of people all across the US, either locally on the computer or, using some other bigger supercomputer or cluster or stuff like that. So what's driving the industry right now is AI and ML, right? So if you can figure out big problems, with QPUs on that end, and then feed it into machine learning workflows or stuff like that, I like say for medical, like you would, besides the noise issue and like the four other issues that I gave, that would be like a brand new technology, as opposed to like, with quantum inspired, it's just like a single, it's just penny lane or Qiskit, and then it's basically like the bits behave differently, right? Everything else is pretty much the same, the linear algebra, matrix vector. But yeah, I'm not as concerned right now as with the bigger problems as opposed to the QiML, the machine learning workflows with quantum. So, I mean, I wish everybody the best, but like, I don't really see that as far as like, okay, we need this device, and now all of a sudden it works, it does batches and, mini batches and all these types of things, epochs and, it's a continuous workflow. It's not just like, we just need this to run. And the other issue is the availability. There's many CPUs and GPUs, but like with QPUs, even if there was something close to a workflow, I don't, that's not going to really, it's just going to be like one person, just like, small groups of people using it. So, yeah, I mean, that's how I did. That's how I define it now. I really do. Like it's either big problem, small data, quantum hardware, or we're talking, real actual quantum machine learning workflows.
Yeah, I mean, I have to agree with you that if you are mixing quantum and classical in the training cycle, that it becomes probably unusable. But I'm thinking more of quantum and classical in the sense that you use the quantum to do certain pieces, and that it's not involved with every cycle of an epoch. For example, support vector machines, there's work out there where they're using quantum programs to craft the kernel. They only do that once per run per
Yeah, I
build.
see. Go ahead.
And so if you can get a quantum machine to build a kernel for enhanced support vector machine, or a kernel for an enhanced principal components analysis machine, and that saves you, by doing that, that could potentially save you uh, an exponential amount of training epochs. Then I think there's some value there. But yeah, I mean, to your point, if quantum is involved with every cycle of an epoch, I don't see that as being viable. It's just the overhead for getting a quantum circuit to run, just just that would probably kill it. But I see it as where the future will be different uses of quantum in extending the machine learning or the AI things, and not necessarily becoming part of the training. Um, so there, and what quantum is really good at is optimization problems. So there'll be some people coming up with discoveries that can use that to craft certain pieces of the puzzle. And again, it probably won't be the parts where it has to run once per epoch. Maybe it runs at the beginning or it runs at the end. It only needs to run once per training task, and hopefully you get better results just by doing that.
Yeah. Yeah, I mean, these are all possible use cases. And like, that could potentially happen. I mean, just like for industries that don't really matter, like, well, I shouldn't say it that way. Like like high, like you cannot like have noise for like a single patient image, So, for other cases, again, what I'm saying is like if for any type of quantum, workflow for like medical, I don't really, it's going to take a lot to accept its results, because there's still going to be noise. And, even if it can crank out, better accuracies it, in a specific way. So yeah, I still see those, but like the revenue generating, or like the primary, focal point is remains machine learning. And there's no other way, it's just like me saying like, well, I believe in neuromorphic computing, and I could have this specific use case that could help. But neuromorphic computing is probably a lot different than quantum inspired machine learning, because it's a different architecture, like on the physical silicon, like the RAM and the compute is in the same spot. Is that a safe thing to do? Those types of things. But I don't, I just don't see a lot of, huge driving, use cases in medical, for QPUs, quantum computers, for at least 5 years, maybe 7. But, you know, you know, I'll get different emails from all these different people, but it's just a comparison over what was previously done, but it's not like, it's not ready for anything that we would consider like, it's just like somebody wants to keep optimizing hyperparameters, at a doctor station. These are things they, to get better results. And just the sheer number of runs, if it's something that's already very similar to classical workloads, like, I think that's where the money in the market's at. I don't think it's, quantum will get better, but like I said, like 5 years is a long time. And I think I would have a hard time finding people that could say like fully noise, like no noise basically, and like, you know, it does differentiation well, we can get the exact outputs, and it can run continuously like how things go today. I think there would be a shift, you know. So, you know, and a lot of it's hinging on these you know, scale ups by Brookhaven and, you know, other NERSC and Nvidia with the help of Penny Lane, and you know, Wall Street Journal, you know, kind of broke the ice with it. So saying that just like GPUs are used in AI, now they're used for quantum. So, you know, to have GPUs working in you know, machine learning workflows that operate by quantum mechanics is awesome. And it, like I said, the architecture of that may be, you know, like it's not actually changing anything classically. It's running classically. But like I said, with like, if we were just to like say, you know, quantum computers, normorphic computing, other types of computing, that's probably a lot different than what we're dealing here, you know, with just a library and just a different explanation of what the bits are doing. But the more we talk about simulators, like dedicated RAM towards simulators, and like these things are different and they need to be treated different, even though that we'll be using them. You know, I think a better use case is just to have a single, you know, a nice GPU laptop, you know, running both classical and quantum algorithms. That's the proof of concept, right? And then we use GPU simulators because they're, you know, separate devices, and we'll use CPU simulators because they have more RAM, you know. But at the end of the day, it's just like, it's basically like I said, it's just it's one extra library with it, you know, Qiskit, Penny
Yeah.
Lane, TensorFlow Quantum, and the outputs are still binary, and it's just, it takes more RAM to simulate. Yeah, go ahead, Ron, and then feel free, anybody else, you know, you can put in the chat or raise your hand. Did you have something, Ron?
Yeah, I was just going to say that, I mean, you had some great numbers for why simulators will be um, running into hard walls very soon. I mean, I don't think most people can wrap their head around how much memory a petabyte is. Uh, you know, I'm in the process of building a new workstation, and I'm probably going to target 64 gigs of core. And then I start thinking, well, maybe I should just max it out. I mean, the motherboards that I can afford are maxing out at 128 gigs. There might be some out there at double that, but I don't even think the memory elements are available. But let's say I could build a 128 gig desktop. 8 of those is a terabyte. So you're talking about 8,000 machines that I could build becomes a petabyte. And then all you have to do to mess that up is, oh, so that petabyte machine will run a 46 qubit simulator. Well, let's add one more qubit. Then that whole facility has to be duplicated because you have to
Yeah,
double everything, and it's getting
but
close to
okay, so
becoming that brick wall. So
yeah, I think, and you're right, like as far as the use cases, they will be different, but I don't think quantum computers have it or will have it anytime because of the noise anytime soon. Now, like traditionally we'll focus on like, you know, feature mapping, you know, separating data. And this has been done in studies like Seth Lloyd and Chris and Temi. There's others too with that. And basically, yes, the different types of utilities will be limited by the overall amount of RAM. And you saw like one of the tricks with this one, as far as like instead of doing things like 16-bit to 2-bit, they get an extra 3 qubits. And yes, when you get up to like,
yeah,
you know, and we're talking about quantum machine learning workflows, we're not talking about like they're just running
yeah.
circuits. So, you know, I think it's a healthy, they say now, like with Penny Lane GPUs, you know, and I think this is even the ones that are scaling it up. You know, they're, you know, typically talking 30 qubits because there's other things going on or could go on as far as like a huge data set that you're putting on, or there's some other like classical load to it all. But yes, the end use cases will be different. Like, as far as these thousands of qubits, but again, hardware is going to struggle with noise and all that type of stuff too. But like, we're talking about like the purest, way of simulating quantum physics, of representing it, because we have no noise. So it is simulating it, but it's a pure representation of quantum physics, because there's nothing else that hardware would mess up. So in some forms, these lower qubit simulators are the purest way of accessing, quantum states, running in QiML workflows, those types of things. But you're correct. Like, there will be limits, very likely, on number of qubits, but the applications I won't be shifted towards those types. It's more like this data over here, this data over there, data re-uploading, these types of things. So
Yeah. Well, I know noise is an issue, but I'm thinking that you might not want to get too hung up on it. If the noise is manageable and doesn't get in the way of accomplishing something, then you can deal with it. Like if you go over and look at the in IBM land with their superconductors, they I don't know if I mentioned this last week or whatever. I just heard that IBM is now making their Eagle process available for on the free tier. And people are like, "Oh, that is so cool," and I know why they're doing it. But the issue with the Eagle is it's a 127 qubit machine, right? It sounds great, but IBM has such a noise battle that you get over a certain circuit depth and your thing is no longer functional.
yeah,
It's just mud. It's just dead in the water. So that at that point, yeah, noise is a problem because it's stopping you from doing anything. But if the noise is at a low enough level where it's manageable, you can still get work done. And
yeah,
even in the QML arena, machine learning is not a precise process, right? You get predictions out of a trained stack. What you get is predictions, right? And they have a statistical probability of being correct. It's pretty much the same thing as what happens in quantum land. So again, if the noise could be kept to a manageable level, we're still seeing people get work done. And again, having said that, I don't see quantum being involved in the training cycles or a quantum process in each part of an epoch of a training cycle. That just isn't going to work well for
yeah,
probably right at least 5 years.
yeah,
But there will be other ways. I'm sure there'll be other ways to use quantum, even with a manageable noisy machine, to accelerate the machine learning in other ways, not being part of that loop, but being part of setup or being part of post processing. So
yeah.
lots of people out there working on these things.
And I think the conversation will shift, because like, if the principal method of machine learning is training, validation, testing, inference, these types of things, people ask, what's the main thing running it if it's quantum inspired? Just all of the attention will go towards it. And again, like, it has to prove itself through, better circuit architectures and better understanding of like big data sets with all this, with quantum physics. If it proves itself, which it looks like it's on a good track of doing, that I truly believe that a lot of the conversation will shift from solely focusing on quantum hardware to these QiML workflows. So, I wherever the results are, and the reason why I pitch for all this stuff is because it's like the money and everything else is, mostly in hardware. So it's like, we shifted back to QiML, and it's kind of stagnated. So 2019, my favorite model is that model from 2019. And I can change things on the classical deep learning. I could change things on the quantum circuit. So it's not like a knock to it. It's just like, the core circuit architecture just, hasn't changed since 2019, and it was made in 2005, with hardware in mind. And it's actually not good for hardware anyway. But I think a lot of us get into quantum computing with quantum hardware, quantum computing, but now we've along found this method that not only can simulate quantum circuits, but it also, does QML workflows very well. It just the numbers have to get better. But as far as they get functioning and all that kind of stuff. But it takes months, and months and months. But that's my thought with this all is basically we're almost at that tipping point where a lot of the discussion will go from quantum hardware not available, for 5 years in QML workflows into now that we can, put more minds behind it, change. I can't change anything in software libraries, but I'm pretty sure I can basically do just gate architecture in it, those types of things. But I see the time coming where it's just, next next QiML workflow, not just like, because it's just you can run it just like you can run, you just need more RAM, in the soft and Qiskit or whatever, but you can run and run and run. And it's like it's not any more expensive in most cases. I've run most of my stuff just like on, well, some stuff needs a GPU, but I see that day coming where it's just like we're talking about QiML. Somebody says, we can have something with quantum that can help on the side of it, and then we'll call it quantum machine learning. But I don't know. There's so many check boxes that have been checked, as far as getting scaled up and its functional technology. NVIDIA, the one that's like behind a lot of like the innovation with AI. Like you can't do AI without like NVIDIA or, some of the other vendors. They're fully behind it. So yeah, I see that coming where everything's just, the standard is QiML. And I wanted to leave room. Does anybody have questions or comments? Anybody that we haven't heard from? I appreciate everybody coming on. And then, so any other last questions or comments here? Definitely fun and exciting stuff. So again, the discussion will be up and on GitHub too. Please like or star the GitHub. Like I said, it's got a ton of stuff. I've had other developers reach out. They say, "Oh yeah, thanks for putting it up." And it's to get to the next levels because like all those notebooks I did, unfortunately, are the same as everybody else, and we need to go to the next level as far as performance and utilities. So yeah, so I appreciate everybody coming on. This has been discussion 107, Thursday, November 2nd, 2023 for QiML architecture, algorithm architecture, R&D, new utilities, and higher accuracies. Have a productive rest of your night and have a good rest of the week, everybody. Take care. Thanks for coming on. Appreciate it.
Thanks, Kevin. Another good collection of info. Thanks.